Cloud services are everywhere today, with thousands of new servers being released every year. Most of these servers can be programmatically accessed via the REST APIs, and through these APIs, clients can create, access, update, or delete the cloud resources. And one important concern is that what security vulnerabilities are there behind these APIs, and more specifically, how to check and find this effectively. Recently, people have proposed the work to perform stateful REST API fuzzing, such as RESTer. So it takes the API specification that describes the available request. For example, you can use a post request to create a blog page, use the get request to update or modify the page, or to use a delete request to remove the page. And given this specification, RESTer will analyze the producer-consumer dependencies between request types, and then generates sequences of requests that allows us to reach a deeper state of the cloud services. So that, for example, it knows that you have to first create a page before you can delete it, or you have to first create to update the page. So with such a stateful fuzzing ability, RESTer can find vulnerabilities like system crash, use sector free, or resource leakage, and so on. However, there's still something that's missing. Stateful fuzzing focuses on producer-consumer dependencies and generating the sequence, but in each request, it sometimes requires a body payload. The body payload is used to provide parameters, values, or some additional inputs, and it can be very complex at some point. So in this work, we focus on how to efficiently generate different kinds of payloads to further explore more vulnerabilities. And specifically, we will study how to generate payloads that satisfy the schema, the spec of the payloads, as well as generating payloads that violates the schema. In the rest of this video, we will first talk about the overall fuzzing workflow, and then dive deeper into the two major parts, schema fuzzing and data-payload rendering. After that, we're going to show our results of applying our data fuzzing techniques for bug hunting in real-world cloud services. In REST API, the body payload is provided in JSON format. The schema specified its tree structure and the type of each node. So it's like the specification of a payload. Given a schema, we will have to render it with comfort values to get the final payload. For example, while the schema only says the node tag is type string, we can render it with either like a local or a global or any other string type values. Given this nature, our fuzzing workflow is composed of two parts. The first one is schema fuzzing, where we take in the original schema and generate a set of new fuzz schema by modifying its tree structures and node types. The second part is once we get the fuzz schemas, we will use different approaches to render the concrete values for the payloads. Let's first take a look at the schema fuzzing. Here, we're going to talk about our basic schema fuzzing rules, which includes node fuzzing rule about how to modify a single node, and include tree fuzzing rules about how to apply across the schema tree. And after that, we're going to talk about combining these basic schema fuzzing rules as a pipeline. Okay, let's first look at the node fuzzing rule. The node fuzzing rule defines how to modify a single node in the schema. Here, we implemented 4 different rules: drop, select, duplicate, and type. When applying a drop at a node, we will remove one child from the parent. So in this example, we get 3 different fuzz schemas when we are applying the drop at the root node. Similarly, we also have select to keep only one child, and we have duplicate to make a copy of the child. So they're more like mostly targeting changing the structures of the schema. The node fuzzing rule type is a little bit different. It changes the type of the node instead of the structure itself. For example, you can change it from string to integer or from integer to boolean. However, there will be some structural side effect when you change the type of an internal node. Like when you change from an array into an integer, all the array items or the child nodes will be dropped. So that's the structural side effect for the type rule. Now that we have these 4 different ways to modify a single node, let's see how to apply them across the tree. The first one, the most basic one, is single, where we only apply on one single node at a time. So the results of this one will be very similar to the original schema. The second one is path. Here we're going to apply on multiple nodes at a time. So we first select a path in a tree, and then we pick some of the nodes in the path. It doesn't need to be all of them, but we pick a subset of the nodes in the path. And then we apply the node fuzzing rule on them. And the last one, the O, which is the tree fuzzing rule O, basically allows us to modify any nodes in the tree arbitrarily. So you can imagine the rule single is simpler. The resulting fuzz schema will look more similar to the original one. And the number of generated fuzz schema is linear in the size of the tree, while the tree fuzzing rule O modify more exhaustively, but the number of generated fuzz schemas can easily explode. Right? So that's the trade-off here. So now that we have 4 ways to modify a node and 3 ways to apply it across the tree, then we want to know which one is the best or which combination is the best. To find out that, we need to measure the effectiveness. And because the cloud servers under test are black box to us, we don't have the access. So we use the error code and error message in the responses as the indication for coverage, and we call them an error type. So basically, we want to have like the more error types, the better. And we use the Azure Domain Name Server, DNS service, as our driving case study. The first observation we had is that different rules can trigger different kinds of errors. The figure here shows that what kind of errors can be found by each rule. Each column represents a unique type error type, and the row, or the points in the row, shows the error types found by each rule. So each point shown on the row means that it can find this kind of error type. For drop and select, they can trigger structural errors that no other rules can find. So we can see that on the left of the figure, there's some error types that can only be found by drop and select. Similarly, type, the rule type, will trigger deserialization errors that, again, no other rules can find, like in the middle of the figure. And of course, for duplicate, we also see this the similar behavior, that it can trigger some of the deserialization errors. But the difference now is that these deserialization errors are due to invalid JSONs or the duplicate keys, right? So because when you duplicate a child, if that parent is key value pairs, you basically create the duplicated keys, and that causes the invalid JSON format. So what we've seen here is that all of the rules are important, and there is no like one single winner for all of them. Okay, besides the node fuzzing rule, now we want to compare different tree fuzzing rules to see if there's a best one. And from the results, we can actually see that it really depends on the node fuzzing rule that we're applying. So we can see that the tree fuzzing rule single works better for type and duplicate, which are the two that cause deserialization errors. And the reason behind this is that once you have the deserialization errors, the processing actually terminates immediately. So it is less helpful or less beneficial to modify this kind of type or in different place in the tree. And for path, on the other hand, it actually works better for drop and select, which are the two that causing the structural errors. So based on these results, at the end, we select 4 combinations as our basic schema fuzzing rules. We have drop, select, type, duplicate with its corresponding best selected tree fuzzing rules. Now that we understand the basics of schema fuzzing rules, let's talk about how we combine them as a pipeline. The idea is actually very simple. We want to combine several rules so that we are not only modifying the tree structures or not only modifying the types. For example, given the original schema, we can apply one rule, such as select, and this will give us a set of new fuzz schemas where the structures have been modified. Then we can take these fuzz schemas as the input and then apply type, for example. And at the end, the resulting fuzz schemas will be modified in both the structures and the type. So that's how we combine different rules to make a more diverse fuzz schemas. Although this idea is fairly simple, one thing to consider here is that it actually generates a huge amount of new fuzz schemas. And because we only have limited budgets, here we propose 3 different search heuristics to prioritize the generated fuzz schemas. We have depth first, breadth first, and random. For depth first, it will prioritize more of the later phases in the pipeline. And for breadth first, it will actually prioritize the early phase of the pipeline. And random is like it will evenly select different fuzz schemas that's generated. To understand whether combining rules is helpful, we again use the Azure DNS as the case study to compare different pipelines. And here, instead of just looking for one that finds the most errors, we're actually looking for one that can find new errors, right? So we're looking for the one that can find something that cannot be found without the pipeline. And from the experiments, we see that there's sometimes like combining structural rules and type is helpful, such as drop type or select type. So on this figure, that's the circle highlighted one, we can see that there's something that can be only found with this pipelining, but cannot be found by just like drop or select or even type, right? And so this is the new thing that can be found only with the pipelines. But however, it's not always helpful for combining rules. So we see that when you combine the rule duplicate with others, the errors we found are basically just the unions of the individual ones. So combining duplicate with other rules as a pipeline is not really helpful. And on the other hand, as I mentioned before, we have only limited budget, so we need to prioritize different fuzz schemas. And to understand how different search heuristics works, we compare them by seeing how they perform when the fuzzing budget increases. So we run both the depth first, breadth first, and also random. And for random, we run it under 5 different random seeds to see how it performs. And our observation is that for random, it actually provides a more stable growth in covering unique error types when the budget increases. So this is definitely more preferable in practical fuzzing. So that's about schema fuzzing. We talked about the 4 basic schema fuzzing rules, about how to modify a node and across the tree, and we explained how we combine them as a pipeline. Now let's change here to rendering the concrete values for the generated fuzz schemas. The challenge in value rendering can be categorized into 3 major aspects. The first one is the lack of class-specific information, such as the user ID or subscription ID. And the second is the lack of domain-specific information. For example, in a payload, it may require you to provide an integer for the service timeout. But however, that this timeout, there may be like an unspecified requirement that this value has to be smaller than 3600. Otherwise, it's an invalid value. And for an automated tool, it's very hard to get this kind of information right. And yeah, the third challenge, besides the first two, is the lack of runtime dependent informations. So for example, you need to point to the right resource that you just created previously. And this cannot be easily resolved by the automated tool. And yeah, of course, it is challenging to get the value rendering right, but why is it important? So we get this figure on the right from the previous experiments. It shows the percentage of tests that trigger each error type. So as you can see that the most frequently found error that takes more than half of the fuzzing budget, the blue one, is due to a wrong value rendering, right? So it's because that we put this fuzz string for every single node that has a type string. And so no matter what's the structures or the type, how we fuzz the schema, it's all kind of like fall into this kind of error. So a lot of the efforts in modifying the structures and types are not efficiently utilized. So this is definitely not preferable if we want to like nicely utilize our budget. In order to improve this situation, we propose different value rendering strategies to try to make things right. The first one is what we already had, a very basic approach that we use for all the previous experiments. It is to have a static type value mapping. So we just fill in the predefined fixed value for every node type. For example, we put a 0 for the numbers and we put false for booleans and so on. So this is a very like the baseline approach. The second strategy is to make use of the examples. So very often the REST API specification also come with like a few examples to show you how a concrete request look like. And these examples, they can be very helpful because they provide the domain-specific information. For example, we know that a valid value of the timeout can be like 10 or so. But one of the drawback here is that this example usually only cover like the smaller subset of the nodes. So it only have the required information, but some optional nodes will not be covered. The third strategy is to learn from the responses. And this can be very helpful because very often the REST API for cloud services has a very rich response. And that response can contain both the domain-specific, client-specific, or even the runtime-dependent informations. But the challenge here is that the responses may not look exactly the same as the request. So we have to have a way to do some pattern matching to find how to learn the values. And here we have two precision levels in matching the nodes. The first one is in a conservative mode, where we only learn a value if it has the exact same path in both the schema tree and both the in the schema tree of both the request and response. And another mode we have is the aggressive mode, where we only check at the leaf level. We compare 6 different combinations of the strategies. We have the baseline, which is using only the static mapping. We have the examples to use the examples from the specification. We also have another 2 that use the responses in the conservative mode and aggressive mode. We also have another 2 that use both the examples and the responses in the 2 modes. And from the results, we can see that using the examples and the responses are beneficial in general, and especially when we use the response in aggressive mode. What's even more is that when we look into the distribution, the value rendering bottleneck doesn't exist anymore. And now the fuzzing budget is being utilized more evenly. Okay, now that we know about how we do the schema fuzzing and about different strategies for value rendering, let's talk about our final bug hunting in widely used cloud services. So based on all the lessons that we learned from all previous experiments, we design our data fuzzing algorithm in 2 phases. In phase 1, we focus on generating payloads that violate the JSON format. So here we use the duplicate rule alone, not in the pipeline, but just like duplicate. And in phase 2, we focus on testing different structures and types of the schema. And it's done in 2 steps. We first use the drop select pipeline to generate a set of tests. We render them using both the examples and the response aggressively. And then we test them, we get the response. And after this, we pick 1 representative for each error type we found. And taking this representative for each error type, we apply the type rule, to generate the second set of tests, and then we test all of them. Using this final data fuzzing algorithm, we had a bug hunt on Azure networking services. And the first service is the DNS service, the one that we used for all the case studies before. And among the 13 request types, there are 4 with empty body payloads, ranging from 2 to 65 nodes. And we found 7 bugs in it, including system crashes. And the second one is bigger. It's a network resource provider, the NRP. And among the 371 request types, there are 49 out of them that have non-empty body payloads. And it's ranging from 2 to even thousands of nodes. So it's a bigger payloads to fuzz. And in this service, we successfully found bugs in 29 request types, including 500 system crashes. And for all of these bugs, we report them to the developers. All of them are being acknowledged, they are reproducible, and they are being fixed or will be fixed shortly. And the details of this bug can be found in our paper. In this work, we show that REST API data processing bugs do exist, even in widely used cloud services. And they can be found efficiently with intelligent data fuzzing techniques. We propose different schema fuzzing rules. We talk about how to modify a single node, how to apply them across the schema tree, and how to combine different rules into a pipeline. We also propose several data value rendering strategies by using examples or learning from the prior responses. And our algorithm that we designed at the end successfully found 17 new bugs in a widely used Azure networking services.